So it feels like it's been a very long time, even though it's only been 2 days. Feels like we've done an awful lot in those 2 days. Okay. So we're trying to find the volume of some kind of funky shape using integrals. And we've got 3 methods to do that. So what's one of those methods? Disks. Okay. So we've got disks. And when we solve it using disks, they're not necessarily round disks like pennies. They may be disks that are differently shaped. They could be squares, they could be triangles. The whole point is that they have a regular area. And then our volume is some integral from a to b of whatever that area is times dx. But remember, everywhere dx is the thickness of whatever it is that we're talking about. Okay, so that's one method. And disks work really well for what kind of objects? Solids. Okay, what's another kind of object we have? Or I'm sorry, what's another kind of method we have to find the volume? Washer. Okay, and when we have the washer, yeah, you kind of have to have a circular. I think in general we have a circular cross section. I suppose you could make it work for something that wasn't a circular cross section. But it basically then again what we're doing is taking some integral from a to b, pi the outer radius squared minus the inner radius squared times dx. Again, dx is the thickness of the washer. Remember that for both of these methods, and really the third one that we'll talk about in a minute, you can always take whatever that shape is and do it in dy instead of dx. So the first step whenever you're trying to find one of these volumes is to actually draw in the washer or the disc or the cylindrical shell and identify what the thickness is, because every other variable that you use will have to be whatever that thickness is. If it's dx, you have to have all x's. If it's dy, you have to have all y's. Okay. And then what's our third method here? Cylindrical shells. And as we'll see, cylindrical shells work for solids. They also work for things with holes in the middle. And the formula for cylindrical shells is, again, this integral from a to b, 2 pi times the shell radius times the shell height times the shell thickness. Okay, and it's that shell thickness, just like I've been saying, that's going to be dx or dy. And then, like we said, again, one of these, usually the radius, is just going to be x or y. And the other will be a function of the function that you're graphing. So, okay, so cylindrical shells are like nesting cups, which is why it works if you have something that has a hole in the middle. You could also turn those cups over and kind of build on top of them, and that would give you something that was solid. That may still give you something that has a hole in it, but that's kind of the idea, okay, is that we're building things up. Okay, so did we finish our first cylindrical shell thing? Oh, yeah, you guys, right? Number 36, you guys were supposed to find the answer? Yeah? Okay, so did you find the answer for number 36? What is the answer for number 36? Okay. If you stayed for AP Physics, I think we finished it because there were some arguments. But, okay. All right, so what I'd like to do is back up to number 29, part B. And if you remember, number 29 was a problem that we didn't use cylindrical shells, but we could. I don't know, Priya. You could look back in your notes because we've already done this problem. Okay, so as you may recall from problem 29, we had a curve that looked like this, which was what? Y equals radical x, that sideways parabola. And we had the line y equals 2 and the line x equals 0. And in part B, we actually rotated it around the y-axis. And we have something that looks like the bottom of a wine glass. Curvy shaped up. What are my cross sections going to be here? Well, they're not just going to be discs, they're going to be a very specific shape. Circles. Okay, so it actually turns out that you can use cylindrical shells for any solid figure that has circular cross sections. So, for instance, down here, I'm going to make a cylinder that looks like this. I'm going to have another cylinder that looks like that. And basically, I'm just going to fill it all in with cylinders. It will look like nesting cups, except that the cups in the middle are very skinny but very tall. And then the cups get shorter and shorter and fatter and fatter. Okay? Not quite like that. I need different colors. Okay? But there's no hole, so there's going to be a very, 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 very skinny cylinder right here at the top, okay? That's going to be so tiny it barely has a radius at all. So I've drawn my cylinders, and what's the first thing I have to do? Yeah, but how do I figure out which way it's going, X or Y? What do I identify first? The what? The thickness. Okay, so this is the thickness of my cylindrical shell. You do the same thing if you're doing a disc. You do the same thing if you're doing a washer. Okay, and so what is that thickness, dx or dy? Dx. And then, like I said, it's usually the radius. And what is that? That green line there. What do I identify that as? X. Good, Sari. That's going to be X. It is the distance from the origin to a point. It's a horizontal distance. So that's going to be X. That's going to be my shell height. What's that going to be? My shell height. Well, let's start with 2 minus y, okay, because this distance here would be the y coordinate of that point that I'm looking at. Okay, and that's this y value. But I don't really want that. I want the other part of this. And because I've got a horizontal line up here, I know that the sum of those two pieces always has to be 2. So my height there is going to be 2 minus radical x once I substitute in. Okay. We good? We got it? So my volume, integral a to b, 2 pi, shell radius, shell height, shell thickness. We'll deal with the limits of integration in a minute. That's my 2 pi. What's my shell radius? It's x. What's my shell height? Good. And what's my shell thickness? dx. So then I have to ask myself what my limits of integration are, and they need to be in the x direction. So what do I end up here? What's that? Well, remember, what's the y value up here? 2. So what's the x value have to be up here? So that point's going to be 4, 2. And remember, it's my radius here that's x. So what value, what's the range of values that my radius can have? 0 to 4. All right, and then we just do this integration. Is that right? No. Yes. Yes. And what's that going to give me? All right, so what'd we get? (32 pi over 5). Thanks, Zoe. And if you look back in your notes, is that the same answer you got? Yeah. So there's more than one way to find the volume. Use the way you feel comfortable with. Sometimes there's more than one way to find the volume, not always. Okay. Use the one that you feel most comfortable with. Make sure that you follow the steps, drawing in the cylindrical shell or the washer or the disc, identifying what the thickness is, identifying all your radii and your height and all the stuff that you need to do. Okay? There are pretty good steps to help you work your way through. All right? We good? Well, you can do this part. You can integrate it, Sarah. Just write down what the answer is and check it yourself. Okay? Because we've got one more thing. I don't know what time it is. There we go. I've got one more thing we need to cover in here, which is surface area. And then did I say when we were going to start 8.4? Is it on the portal for tomorrow? Okay, I think it's tomorrow. I have in my planner that it's tomorrow. Okay. Because we've only got 3 more sections to go and I really want to be done before spring break. Okay. Okay. So to look at surface area, let's look at page 413, number 59. If somebody wants to read it for us, please. Okay. Thank you, Sarah, for being a good community member. Okay. So, always good to start by drawing a picture. Y equals x squared is a what? It's a parabola. Okay. So there's my parabola. I'm going to go out as far as x equals 2 because that's what I'm supposed to do. This is the area under my curve. And I'm going to rotate that about the x-axis. So I end up with something that looks like that. And again, it's the same kind of thing we've been looking at. It's a curvy-sided cone. So instead of having straight sides, like an ice cream cone, it's almost as if I've kind of plucked it up and there's like goop hanging off of it. Okay? And I want to find the surface area. Well, exploration 2 gives us info on how to find surface area. So what we do is we take a strip that goes all the way around. Looks something like that. And if I unfold the strip, I get something that kind of looks like that, which kind of sort of looks like a rectangle, except it's kind of sort of not entirely a rectangle, but it's pretty close to a rectangle. Okay. And then I say that the thickness of this rectangle is delta S. Not delta X or delta Y, because it's kind of on an angle. And what I'm going to end up saying in a minute is that I'm going to use the Pythagorean theorem, which tells me that delta S squared is going to be delta X squared plus delta Y squared. And if you've been paying attention for the last 6.5 months, you should anticipate that I'm going to turn those delta x's and delta y's into dx's and dy's, and then I'm going to make my strip really, 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 really narrow, and then I'm going to add them all up. Okay. What's this going to be? Yeah, it's the circumference. And what's the formula for circumference? 2 pi r. So I'm going to need to know what r is. And so r kind of looks like that. And what's that kind of going to be? So yeah, kind of. It's like I said, it's going to go away in a couple of minutes. Okay. So what's that? This is my radius here. What is it? Y. Okay. Or f of x. I don't know why, but your book calls it f of x, probably because we're going to add things up. So the area over here is going to be the circumference times the width, right? Length times width, because I'm approximating it to be a rectangle. So this is going to give me 2 pi f of x delta s. But since we all know, because we've been around this block a couple times now, that eventually I'm going to want to add up all of these tiny little strips of area that I'm going to want to integrate. And my delta whatever is going to become my d whatever. So if this becomes ds, and this is f of x, well, that's going to be a problem, right? Why is it going to be a problem? My differential and my function have to have the same variable. Okay, so that leads us back to this. So I'm going to write that again. So, except that this time I'm going to write it as delta s is the square root of delta x squared plus delta y squared. Because delta s is what I ultimately want anyway. So I'm going to factor out delta x squared. I factored out a delta x squared. I have one delta x here. I don't have any delta x's there, so I have to divide by it so that when I distribute, I get that back. Right? Delta x squared times 1 gives me delta x squared. Delta x squared times delta y squared over delta x squared. The delta x squares cancel, and I have delta y squared. Because I've squared the whole thing. Okay? Because what's this? Delta y over delta x. What? I wasn't quite going to go that far at first, but yes, because what is delta y over delta x? Slope. And then Casey, the slope of the tangent at the point is the derivative. Okay? So if I make everything small enough, which I'm going to do, then yes, that is going to become the derivative. So, and also what I can do is now I can bring this delta x squared out from under the radical, right? And what's it going to become? So I got delta x times the square root of 1 plus f prime of x squared. Okay? With me? Pretty much just algebra so far. All right, now let's go back to that formula that we had for area, which said that we had 2 pi f of x times delta s. And actually what I should really do is say this is the area of the kth strip and let it be f of x sub k. So that I can add them all up and then integrate them. Okay. So the area of the kth strip, 2 pi f of xk. Now I can substitute in that other thing for the delta s, which is delta x times the square root of 1 plus f prime, again, of xk squared. Bless you. And if I want to find the total area, I have to add up all the AKs. And of course, I want to take the limit where delta x goes to 0, right, of my sum. And when I do that, what do I get? When I make my strips so tiny that they're infinitesimally wide, what does my summation become? An integral. So this becomes an integral, again, from some a to b of 2 pi f of x square root of 1 plus f prime of x squared times dx. And that gives me surface area. So in the problem that we were looking at, what was f of x equal to? X squared. So Gianni, what's f prime of x? 2x. So if I'm supposed to find the surface area, that's going to be the integral. We'll talk about the limits in a minute. 2 pi f of x, which is x squared, times the square root of 1 plus f prime of x, which is 2x squared, times dx. And then what are my limits of integration? 0 to 2. Good, whoever said that. Okay. Now, that is a nasty looking integral. I'm not sure I could do it. I could. But really, you could also use numerical integration on your calculator. So why don't you do that and see what you get. You're going to forget about what? Well, you can only do it sometimes. Mm, mm, mm. 53 point something. What'd you get, Gianni? Same thing. Okay. Yeah. The calculator seat over there. That's the problem. Okay. All right. So tomorrow we start 8.4. The homework is due on Thursday. If you want to turn your homework in early, I'm happy to grade it early. For the 8.1 to 8.3, that's due on Thursday. We got 3 more sections to go, and we're done. And then we can review. Nope, but we have to go back and we have to go ahead and do L'Hopital's World, which is chapter 9.